G'day. So what we're going to do this morning is I'm going to show you how to use the Movires theorem to solve what looks like a fairly hard polynomial. So the solutions of these are going to be in complex form. So we're told z is cos theta plus I sin theta. We're going to solve this. So what we do when we see this sort of questions, the first thing we want to do is we want to make all these z to the power 4, z cubed, z squared, etc. a little bit easier to deal with. So what I'm going to do is I'm going to divide by z squared. Now what dividing by z squared does is it changes it to this. So divide by z squared, we get a z squared there. If we divide 8z cubed by z squared, we get a z. We get a plus 11, we get a minus 8 to the z minus 1, which is just a 1 on z, and we get a 4z to the minus 2 equals 0. And then what we're going to do is we're going to group them together. So I'm going to put these two together because they've both got a factor of 4, and I like getting z squared and z to the minus 2 together, and I'll show you why that's good. The same with this is really a 1, so I'm going to get that and that together, and then I'm going to have this one by itself. So I'll get 4z squared plus z to the minus 2 minus an 8z plus z to the minus 1, you can put a 1 there if you like, plus 11 equals 0. So what I'm going to do now is I'm going to show you a little bit about this z squared plus z minus 2. Now you don't need to do this every time you solve these, but I'll do it the first time now and you can see why it works, and then you can just go straight to this step that I'll show you where you can go to. So let's consider z squared plus z to the minus 2. Now, using de Moivre's theorem, if z is cos theta plus I sin theta, then z squared must be, remember the modulus is just a 1, so we don't have to worry about that. We get cos 2 theta plus I sin 2 theta plus, now if the power is a minus 2, de Moivre's theorem still works, so we get a cos to the minus 2 theta plus I sin to the minus 2 theta. Now what we're going to do is we're going to have a little bit of think about what this part here can simplify to and what this part here can simplify to. There's some trig properties that you should be familiar with. I'm just going to draw them over here, that the cos of minus a is actually equal to the cos of a. Now we can have a bit of a discussion as to why that's the case. And the same thing with the sine of a negative angle. It's equal to minus the sine of a. So what that means is I can actually replace, that's just something I'm remembering, cos minus 2 theta with just a cos 2 theta, and this here can get replaced with something as well. So what have I got? I've got cos 2 theta plus I sin 2 theta plus this becomes a cos 2 theta. This becomes a minus I sin 2 theta if I bring the negative out, and these two can cancel. So what I get left with, 2 cos 2 theta. Now we can do exactly the same process with z plus z to the minus 1, this little part here. So we get cos theta plus I sin theta plus a cos minus theta, you can put that in brackets if you like, plus an I sin minus theta. Now again, using these properties up here, we know that that's going to be replaced with a cos theta. This will become a minus I sin theta, and again that and that will cancel. So I'm just going to jump straight to the process here where we get this as 2 cos theta. So if I then replace z squared plus z to the minus 2 and z plus z to the minus 1 with these two expressions, this equation here that I'm trying to solve now becomes 4, times 2 cos 2 theta minus 8 times 2 cos theta plus 11 equals 0. Now a little bit of expanding, we get 8 cos 2 theta minus 16 cos theta plus 11 equals 0. Now we've got to solve this equation. Now we're getting pretty close to having it all in terms of cos theta. We're not quite there. This is a cos 2 theta. So what I'm going to do is I'm going to use your trig identities that you've learned from extension 1 and replace that with something. Now remember, cos 2 theta, you don't need to write this out all the time you do these, you just write down what you're doing, has 3 identities you're familiar with. So there's the cos squared theta minus sine squared theta, there's 1 minus 2 sine squared theta. The one that I'm going to use is the one which is in terms of cos theta, which is that one there. So this becomes 8 2 cos squared theta minus 1 minus 16 cos theta. I'm just going to rub that out so it gets out of the way, and plus 11 equals 0. Again, expanding, we get 16 cos squared theta minus 8 minus 16 cos theta plus 11 equals 0. Bit of simplifying, we get 16 cos squared theta minus 16 cos theta plus 3 equals 0. So use some crossbones. So I reckon on this side we're going to have a 4 cos and maybe a 4 cos. On this side, because there it's a positive and that's a negative, we're looking at probably both negatives. And just a little check, minus 12 cos theta minus another 4 cos theta gives you minus 16 cos theta. So the factored form is going to be 4 cos theta minus 1, 4 cos theta minus 3 equals 0. Now what I'm going to do is I'm just going to write down for what values this holds true, what are the solutions to this are. So we get cos theta equals a quarter, and we get cos theta equals 3/4. Now this is really good because what I've got is I've actually got what cos theta is as a solution to what I'm trying to find. So I've got this little part here. I need to get an expression for sine theta. Now sine theta in this case can be a little, you need to think about it a little bit more. So remember, if cos of the angle is positive, it could be in the first or the fourth quadrant. So sine could actually be positive or negative. So you actually need to get two parts. It's not just enough to draw one of those little right-angled triangles, because that's only if everything sits in the first quadrant. So what I'm going to do is I'm going to use this property. I'll write it here and then I'll rub it out. But you know that sine squared theta plus cos squared theta equals 1. That means that cos squared theta, well, sine squared theta is actually equal to 1 minus cos squared theta. Now if I find the square root of both sides, I get sine theta is equal to plus or minus the square root of 1 minus cos squared theta. Now I know what cos theta is. I've got an expression here. So if I substitute this into that, then I'll be able to get an expression for sine theta. Again, I'm just going to rub that out. And then what I'm going to do is I'm just going to write down this, since sine theta is equal to plus or minus the square root of 1 minus cos squared theta, that's just rearranging your Pythagorean identity, we can get sine theta on this side equal to plus or minus, so it's going to be 1 minus cos theta all squared, so that's a 1 on 16, so we get a 15 on 16 on the square root sign. The square root of 15 I don't know, well it's irrational, but the square root of 16 I do know, so I'm going to put it over a 4. If I use cos theta equals 3/4, we get sine theta equals, so 1 minus 3/4 squared is 9 on 16, 1 minus 9 on 16 is 7 on 16, so we get plus or minus root 7 on 4. So combining this bit of information, there's one solution, there's another solution. If cos is that, sine is that. That means the solutions to this equation are of two forms. Remember, it's of cos theta plus I sine theta. So these have both got denominators of a quarter, so I'm going to write it all over a common denominator. I get 1 plus or minus root 15 on 4. This has got an I with it as well, because there's I up here. And the cos theta of this side is 3/4, so it's going to be 3 plus or minus I root 7 on 4. Now they're the four solutions to this polynomial for that question. Good luck.